We in the last class we have covered up to FPGAs, right, where we have seen how different logic functions can be implemented using FPGAs. You will have further lectures on hands-on on Xilinx platform and some lab activities as well. I mean some VHDL and other things as well. Now, today we will be talking a little bit more on embedded system hardware, and we will be essentially looking at sensors, actuators, and other things. So, I know many of you are scared or have an apathy when you hear about hardware, but in embedded system you cannot escape hardware because of the simple reason as is shown here. As before, I will be relying on Professor Peter Malvedal's slides, the book that I have referred to you in this lecture. So, as is said here, the development of embedded system cannot ignore the underlying hardware characteristics, okay, because of the reasons that we have to give real time behavior, efficiency, energy, security, reliability. So, energy, battery and all those we have to think of how the hardware has to be designed. And now in security, earlier we are talking about encryptions and other techniques. Now people are talking about different hardware means of security to resist against different types of attacks. It is even being tried that if the attacker wants to change the pattern of attack, then there are hardwares which are sideline channels using got a special hardware to guess what is the pattern in which the attacks are going on. So, all of these things are will come under the purview of our embedded system design. Now, coming back to the old scenario, we have seen that we have got a physical environment, right. We have got a physical environment which we want to control. And this environment, because of its own nature, will have some physical parameters. For example, if the environment that I am dealing with is temperature, then temperature has got some features like it is sluggish, all right. The range is, there is some specific range. On the other hand, if it be pressure, then the range is something different, right. So, we want to actuate the physical environment by some means. We want to actuate it by some means, which is, say, let us call it the actuator. Now, we want a particular performance from the physical environment, say the temperature or something, and for that we need to sense the environment using proper sensors, right. And this sensing, we have done it in an earlier lecture, that once we sense, we can, if my information processing is digital, I will be doing some sort of information processing here. Later on we will see that it is also controller in some, for some applications. If we do some information processing here, often it is needed that this information processor gets the signal in the digital form. So, we will need A to D converter and will get the information, right. So, we get that information, and after processing the information, we will actuate it. We will take some decision and we can actuate it. We can either do display here, some sort of display here, or we can actuate it. Now, depending on the actuator, there are some digital actuators which can be fed directly fed the digital signal, but otherwise if it is not so, then we will be needing a D to A converter here. And of course, there are parallel paths. So, if it be a digital sensor, then I can directly have it without bypassing the A to D converter, and if it be a digital actuator, then I can also bypass this by feeding it directly to the actuator. Now, in order that the performance of this entire system is up to the level that is expected, the desire, not only your information processing algorithm should be correct. Of course, the information processing will algorithm will have to respect the real time constraints, if any, the power constraints, if any, but say for example, whenever we are talking of power constraints, we will see later that the power consumption or the energy consumption of the battery life does not depend on the hardware alone, it also depends on the software. We will show you that. But along with that software part, the hardware that we are using for all these are also important. The power consumption of different analog to digital converters will be different. The speed of the different analog to digital or digital to analog converters will be different. So, we will have to select these also very carefully. Very important is the selection of sensors and the actuators. The sensors come in different forms, and I will put in a self study material for you today, where you will have to learn more, dig out more about sensors. I will give you the reference at the end of the class. Now, the sensors can come in different forms and for different reasons. For example, what are the types of applications that we may need? Say the physical processes that we are talking about. Okay. We may like to say here a couple of examples, like say heating a room. Okay. So, we will need to sense the temperature and control. Similarly, you may like to control the light. What type of sensor would you require in that case? You will have to have some sort of light sensor. How you can sense light, we will see. And accordingly, you will have to actuate the light controller to control the light. Similarly, nowadays it is becoming practically omnipresent in every car, that is engine control. Now, here in engine control we can sense so many parameters, you can guess some. One is of course, the speed I can sense. Okay. This will also require the temperature of the engine, what is the status of the coolant, maybe that speed and RPM are this E. speed and RPM, these are coming up. It can be the gear, it can be the, now when we sense the speed, we also often may need to sense the friction of the road, because we want to maintain the speed, and as the friction of the road changes, our applied force will have to vary, right. Nowadays, not only in engine, if I just extend it to automobile control, then you will have to sense the door locks, the door status, the belt. Often in every car nowadays we find that whether we have owned the belt or not, that they are showing. So, all those are different sensors. Very important thing is the on impact, the airbag comes out. So, I would rather say now it is airbag, tomorrow it may be something different. So, impact we have to sense, right. Braking control, right, ABS systems where we have got braking control, and so on and so forth. So, these are very important. I mean, automobile is becoming a very interesting and lucrative also from the commercial angle for application of embedded systems here. Now, also another thing is that, okay, we are talking about power, but we will also have to control the power supply. We will see later. We will see later that in order to minimize the power consumption in a system, battery life, in order to maximize the battery life, we will have to control the power supply. All right. So, it will have to look at the power consumed at different parts. It will also have to look at the activity pattern. All those things have to be sensed, and accordingly you change the power control. And a very popular among the students is the robots, right. Nowadays, we have heard of robo-soccer, right, where the robots are playing football. So, where we are giving them the ability to see the ball, see the opponent players, and accordingly apply the information processing algorithm to find the maneuvering maneuver the movements, right. So, there are so many different parameters that we may like to sense. Even we may like to sense the or find out what is the chemical composition of a compound, what are the things. For example, I want to, that will be a very interesting project for all of you. If you can make a small system which will take around and put it wherever you find water, you just put it in and look at the measure the quality of the water, right. Very simple and not very simple, not at all simple, because you have to find out the proper sensors, and then you have to first of all take the water, analyze it through the sensors, and find out through your information processing mechanism. Accordingly, you can generate alerts and all those things. So, we may need to, besides the typical velocity is one we may like to sense, acceleration, weight, temperature, electrical current, all those things. We also need to find out the may be applied for chemical compounds and all those things as well. Next, so say for that we have got different sensors. Some of them we can have a look at here. Here is an accelerometer. Okay. Nowadays, this accelerometer comes in different, even in our phones, right, where we have got gyroscope and all those, but you never thought what is the sensor that has gone inside. So, that we will have to find out, all right. So, actually there is a small thing that moves this thing, and the rate at which it moves, from there we find out what is the acceleration. So, there will be it can be a magnetic sensor. Now, there are different ways of image sensors, which are there often in cameras. Now, they actually come in two forms. One is say CCD image sensors, where we have got the charged coupled device here, and depending on the light, there is a physics that takes place in the semiconductor level, and based on the charge transfer, this works. On the other hand, there is another one which is a CMOS based image sensor, I am sorry, where we have got an array of images being sensed in the rows and the columns, and we are having an analog multiplexer, and we are doing the analog to digital conversion and all those things. Now, both of them has got their pros and cons. Some are VLSI technology and CCD is optical technology. All right. In CCD, there is no logic, so that you cannot put in smartness over there, whereas in the CMOS one you have got logic on chip. Power consumption for CCD is low, but for CMOS it is higher. So, you will have to look at, say for example, I am trying to sense image, you have to decide on what sensor I will be using, because you will have to look at different contending parameters, the parameters which are conflicting among themselves. So, you will have to weigh it out, just like that has to be done by engineers at all stages, right. So, here is a fingerprint sensor, right, that is often used. Now, this is very interesting, this sort of sensor, which is experimentally it has been done. You can see that some person who is blind, they are having a camera, and that image is being processed, and with some sensors it is being fed to the occipital lobe of the brain. Okay. Now, this is the electrodes, they are non-invasive or it may be invasive, there are different experiments being done, and thereby whatever the camera is capturing. So, that is also a sensor. Okay. Another nice application could be that there is a camera here, and you just do not invade the brain straightway, you just do not invade the brain, but you convert it to sound. Okay. Now, say in India, say for example, the blind people are moving around, and they have got you have seen blind people moving with canes, right, and that cane they move like this to sense whether there is any obstacle or not. Now, systems have been designed here in India, where people have tried, and some of them are also commercially available. One developed at IIT Delhi is commercially available. That is, the stick also has got a camera, and the camera is sensing. Okay. It is at the gross level, it is identifying whether how far the object is, whether it is a moving object or not, and accordingly it is giving some pre-stored messages. A more sophisticated thing can be that it will, suppose I have got the image recognition capability coming up, then that sensor, the camera is sensing the image, and in real time it is saying what is there in front, okay, and accordingly they can maneuver themselves. So, here is an attempt, that is translation in sound. You can look at this, seeing with sound, and you can see the typical features of this system. There can be, you can think of several such applications, where you can help these people using embedded systems. Next, let us come to some now whatever we are sensing, we are sensing the proximity, maybe with the proximity with the stick, how far the object is. The carts can also have proximity sensors to find the distance, and accordingly the speed can be controlled. You can think of many such things. Now, in all these things, what the sensor is sensing. First of all, there are two things we have to know about the sensors. One is what are the sensor parameters. I will take a second's time to see if I can give you some reference here. It seems to be too slow. Yes, you can let me write down this. Not this one, yes, this one will also do, either of them. Why is it so slow? So, I am just writing down mimsindustrygroup.org. If you go over here, you will find the standardized sensor performance definitions. All right. If you go down this page, you will find this, and if you go here, you will find a SPD version, the first version of this. It has a consortium has been formed, and that consortium has decided on this. It is taking too much time, where you will see that for the different parameters, different types of sensors, what are the things that are required to be known. Okay. So, here you see that these are the first drafts and etc. Now, you come, say for example, you come to accelerometer here, all right, you can see that accelerometer. Now, for accelerometer, what are the parameters? Full scale range, digital bit depth, sensitivity, noise, all those things you have to, all these things are important. Similarly, for magnetometer, what are the parameters that are important? So, you have to learn about this. Gyrometer, what are the parameters? How do you specify? Barometer. So, in that way you have got several of these things, and I insist that all of you go to this site and read through this document, and in this document you look at what are the parameters that will give you an, you need not memorize, you can understand that why this is needed. For example, let me just mention some very fundamental parameters. What is meant by resolution? When we talk about resolution, what does it mean? Yes, resolution means the smallest identifiable element. For example, if I have got, for example, a voltage, I am measuring voltage through some digital means or analog means, and my voltage range is from 0 to 12 volt. Now, it can be any voltage, right? It can be any voltage within 12 volt, and I want to measure voltage at any particular point of time, and the actual voltage is this, right? And at this point, if I want to measure it again, the actual voltage is very close here. Can I differentiate between this voltage and this voltage? On what does it depend? Suppose I am measuring it using a 8-bit sensor. So, what is the level of how many different levels can I distinguish? It will be 256 levels or 0 to 255. So, 256 levels. So, what will be the resolution? 0 to 12 volt. So, 12 by 256, whatever that is. All right, anybody can compute and tell me? 12 by 256 quickly. So, it will be around 1 by 20, so around 0.5, right, coming to what? 0.046, 0.05, right? Yeah, so 0.046. So, this, right. So, I can distinguish between these voltages, right. So, I can distinguish between 12 and or say 11 and 11.046 volts. In between, if there is any, if these two are close by, closer than 0.046, I cannot capture it. So, that is what is resolution. We must look at the resolution, looking at how closely I want to monitor it. The other thing is, of course, stability, range. What is the range? Say I take a sensor or I take a temperature. What is the temperature range it can sense? There are, whenever I am trying to, there is another thing, the skew rate with or temperature sensitivity. With temperatures, how does it change, right? It's now, if we always prefer a linear range, right? If there be something that is linear, then I would rather prefer to operate in that linear range, where this is my physical signal and the output that I will get from the sensor will be linearly related to the physical parameter, right. So, these are, we also have to check for the linearity. Up to which range is it linear? After that, its linearity is lost. So, all these things we have to look at, and you can study this MEMS. For those of you who cannot read this, MEMS industry group, MEMS industry group.org, and you can look at into that. So, that is one aspect of the sensors. The other aspect of the sensors is that what do the sensors do? The sensors generate signals, right. They always generate signals. And what is a signal? A signal S is can I write this? A signal is a mapping from the time domain to a value domain, right. Some signal is going on like this, some physical process is going on like this, right, and I read the signal, my sensor is reading the signal. So, it is taking at any particular time, this is the time axis and this is the value axis. So, at any point of time I sense it and I get a value, right. That is what the signal does. Now, this is analog, this is a continuous signal. Now, this time is also continuous. Now, theoretically I can map from the continuous domain to the continuous domain, or but for all practical purposes what we do is we need to do discretization, right. So, we want to do discretization of time. We are not discretizing the signal, we are trying to discretize the time. All right. Now, how do I discretize the time? How do I discretize the time and yet get the value? For that, we need, okay, let me just come out of this and come back to where I was. Okay. Now, so when I discretize, I need to do something like sample and hold. Okay. That is something that is very important. We will show that. Many of you from with electronics background may be aware of this sample and hold circuits, but just for the sake of completeness, let us discuss it in this context. Now, suppose I have got something like this. Here is time t, and I have got a signal, and on this side I have got the value, and I have got a signal like this. And let me call this signal some event E t, it is varying with time, all right. And I want to sample it at specific times, at fixed intervals, I am sampling them. So, I am getting a series of discrete values, because I do not know what is the value in between, right. I am getting some sort of discrete values. Now, what does your, as long as I do not know what is the next value, the value that is there in my memory is this. Therefore, now, so this is the sampled value, these values. So, this we call H t, or the value that has been sampled. Okay. So, if I have a circuit like this, do not get scared with the circuit, it is a simple transistor 1, and I have got a clock here and a capacitor here, school level knowledge. So, I give the signal E t, this signal is coming over here, and whenever I want to sample, at those times I feed the clock, tuck, 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 all right. As I feed the clock, this transistor is closed. So, it passes here, it passes. So, that means every time I put the clock, I am sampling it here, 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 like that. And as soon as that is closed, it is current is flowing and charging this capacitor. And so, this capacitor will therefore hold the values at each of these points. And how will it look like? If I take it, as long as the new sample is not there. So, this value, whatever this value I am just trying to guess, this value is here, then this value will be, lower value will come, then an intermediate value will come, like that. These things will be sampled and it will be held, sample and hold, the holding is being done in the capacitor. So, this is being held here, because I have got no idea what happened in between, right. So, in that way we will get a sort of digitized version of the same signal. So, by this sample and hold signal, what I am doing, I am transforming a continuous signal. So, let me draw it a little bit more, then it again came down to some value, then it again went up to some value, like that, all right. Now, so I had a continuous signal E t, I have converted into HT, or that is the discrete signal. Okay. So, for discretization, one very important thing is to get the sample and hold circuit. Now, the $1,000,000 question is, when I am doing this, am I losing some information? Yes, and may not be. So, how do you do that? How can we approximate a signal? And yet can say that with whatever information I get, I can reconstruct that signal. Exactly. Yes, for that we will discuss that in detail tomorrow, but in the next class. But it is if the rate of sampling, it was established by the famous Nyquist theorem by Shannon, that if the rate of sampling is greater than equal to twice the highest frequency of the signal, then we can reconstruct the signal. So, that thing where, say for example, here is an approximation of a sine wave. I will just start it today and we will carry it on in the next lecture. So, here we have got, my objective is, say I want to generate a square wave with a period 4, all right, and I am starting with a sine wave. So, a square wave with, I am starting with a sine wave, right. Now, if I here k is equal to 1, if you just look at this equation, the period is 4, so 4 by pi, okay, sine omega t, and the period is 2 pi by pk is my omega. So, here if I put pk to be 3, then this waveform becomes this, all right. I first, now if I make it k equal to 1, then it is simply a sine wave, right, k is 1 and pk is 4, and you see the period of this is from here to here is 4, right, from here to here, the same phase, the signal is in the same phase. So, it is 4. Now, if I increase the k value, then you again see the period is still 4, but we have approximated it a little bit more. Now, if I increase it further, I make k equal to 5, then the same signal, I mean same equation will yield me this with a period 4. Okay. As I go on increasing, k is 7, then again the period is 4, gradually I am approaching a square wave, that was my intention. So, starting with a sine wave, I can reconstruct the signal. So, I can create a, so I was trying to approximate a square wave. Now, my point is, I want to approximate a square wave. As I go on, you see k9, k11 is gradually becoming more and more of a square wave, right. So, thereby it is possible to approximate a desired signal with a set of other signals. We will continue with this in the next class, and we will see a little bit of how we can do the reconstructions and proceed with a little bit of communication in the next class.